Hey Calc BC, today's lesson is lesson 2.2, the second lesson in unit 2. We're talking about the chain rule and implicit differentiation. To give you a bigger picture here, remember this is the second of 4 lessons in our unit on A-B derivatives. So we're going to be working through the College Board's versions of units 2 through 5 and hitting on a couple key things. Today's lesson specifically is going to be from the College Board's version of Unit 3, Lesson 1 on the chain rule, and Lesson 2 on implicit differentiation. There's going to be a lot more stuff mixed in as we go, but those are the key things that we're going to hit on. So without further ado, let me switch over to the notes. All right, so again, we're going to be looking at the chain rule and implicit differentiation today. So let's not waste any time. Let's get started. We're going to find the derivative. Do not leave negative exponents or complex fractions in your answers. So let's take a look at this first one. Now, before you learn the chain rule, what you might need to do here is actually multiply 4x cubed plus 3x minus 2 by itself 5 times, and then find the derivative of each term using the power rule. But we don't have to do that. We have the chain rule, right? So the chain rule means we treat this function to the fifth as an outer function, and we take the derivative of that, leaving the inside alone first. So we're going to do 5 times, leave the inside alone like it's just one variable. We reduce the power by 1, right? So that was the outer function, was this thing to the fifth. So we took the derivative of that, just like we would with the power rule. We have 5 times the thing to the fourth. And now we multiply by the derivative of the inside, right? So the inside is 4x cubed, so the derivative of that is 12x squared plus 3 and 0. So there we go. And we can leave it like that. So that's our first derivative. It took us, what, 10 seconds instead of minutes that it would have taken if we multiplied this by itself 5 times and then took the derivative. And we could multiply, reduce all of this if we wanted, but we don't really need to. And we don't have any negative exponents or complex fractions, so we're good. Let's keep going to letter B. The first derivative. Okay, so I'm going to start by, instead of thinking of this as a quotient, I'm going to rewrite it as negative 7 times 2x minus 3 to the negative 2. And that way, we don't have to deal with it as a quotient. So now we're going to once again use this chain rule. So we have the negative 2 times the negative 7 is positive 14. The 2x minus 3 stays for now, and we subtract 1 from the exponent, so it's negative third, and we multiply by the derivative of the inside, right? So the inside 2x minus 3, the derivative of that is 2. And so we have 14 times 2 is 28 times 2x minus 3 to the negative third. And we don't want any negative exponents in our final answer according to the directions. So we're going to have 28 over 2x minus 3 to the positive third. And that's our first derivative. Let's do the same thing for the third question. So we have, starting out, 5x times x squared plus 2 to the negative 1/3 power. And we have a product here that's unavoidable. I suppose we had a quotient in the original, and we could have thought of it as staying as a quotient, but we'll get the same answer either way. But that's going to be our u and our v. Actually, we might as well just keep the 5 with the x. So 5x is going to be our u. X squared plus 2 to the negative 1/3 is going to be our v. So let's see what we get here. So first I'm going to do u times the derivative of v, which is going to involve the chain rule. So we're going to have negative 1/3. So this is times negative 1/3 x squared plus 2. Negative 1/3 minus 1 is negative 4/3. And then we multiply by the derivative of the inside, which is 2x. And then we're going to add v times du. So we have x squared plus 2 to the negative 1/3 times the derivative of 5x, which is 5. Okay. So what's going on here? We have 5x times 2x is 10 times a third. So we have negative 10 thirds times x is x squared. And then we have this nonsense here. So we have x squared plus 2 to the negative 4 thirds plus 5 times x squared plus 2 to the negative 1 third. Right? And what we need to do next is finish according to the directions, which is make sure we don't have any negative exponents. So I'm going to write this as negative 10x squared over 3 x squared plus 2 to the positive 4 thirds plus 5 over x squared plus 2 to the positive 1 third. So there we go. All right, so that's an introduction to the chain rule. Let's see what happens next. We're going to introduce trig with the chain rule, right? So don't forget, here's our trig derivatives, and we can remember sine and cosine with Santa Claus, negative Santa, negative clause. We can remember tangent and secant using pst and take out the p, so it's SST, so it either goes TSS or SST. And for this one, we can remember negative cot, right? So we have the derivative of cotangent is negative cosecant cosecant. The derivative of cosecant is negative cosecant cotangent. And that's from cot. And this one over here is SST. And the ones up there are Santa Claus, negative Santa, negative Claus. Okay. So let's do some chain rules. So here in letter D, y equals cosine of 3x. So we take the derivative of the outside. This time the outside is cosine. So the derivative of cosine is negative sine. So we have negative sine of 3x. We keep the inside the same, remember? And now we multiply by the derivative of the inside. So that would be 3. And I'm just going to leave it like that. But we could rewrite it as negative 3 sine of 3x. In letter E, sine of 5x squared. So the derivative of sine is cosine. And then we take the derivative of the inside, so it's going to be times 10x. And for this last one, the derivative of cosecant is negative cosecant cotangent. So we have negative cosecant of 7x to the 5th. Cotangent of 7x to the 5th times the derivative of 7x to the 5th, which is what? 35x to the 4th. Right? And you can even see up here, this is written out in a chain rule kind of way where we were using u. And so we have du dx at the end, which is what we did without referring to it in that notation. But let's keep going. With trig functions in letters G and H here below, where the trig function is raised to a power, the chain rule means that your derivative will be found by the power rule times the derivative of a trig function times the derivative of an angle. All right, let's talk about what that means. So here's what we're thinking about. Cosine of the 4th of 5x. If I wanted to rewrite that in standard exponent notation, it would look like this. We have the cosine of 5x raised to the 4th power, right? That's what this notation really means. This whole thing is raised to the 4th power. So this description right here is saying that we have an inner function, the 5x, a mid function, which is the cosine, and an outer function, which is the 4. So our chain is now 3 links long. We have 3 portions of our chain. So the outer part is going to have to be 4 cosine of 5x to the 3rd, which I'm going to write here because that's our standard trig notation or trig notation. And we multiply that by, now we're at the mid chain. So the derivative of cosine is negative sine. And then we get to the middle, and the derivative of 5x is 5. Okay, I could leave it like that. If I wanted to, I could rewrite this and combine the 4 and the 5 to make negative 20, but we don't need to do that. Let's take a look at H. So now our outer again, we can rewrite this as this squared. So the outer is now the exponent of 2. So we have 2 secant of 4x cubed plus 5 to the first, right? We've reduced the power of 2 to a 1. So it's written like this. Multiplied by the derivative of secant, which is secant tangent. So now we have secant 4x cubed plus 5 times tangent of 4x cubed plus 5 times the derivative of the 4x cubed plus 5, which is what? 12x squared. So after all of that, we have this mess. Again, we could reduce this. We have 2 secant of 4x cubed plus 5, so that could be written as secant squared. The 2 and the 12 could be combined and multiplied. But I'm just going to leave it like that in its initial form. There was a 3-part chain. We did all 3 parts, so we're good to go. Let's keep going to the next page. All right, letter I. Y equals tangent of sine x. Okay, so we keep going. Our outer function this time is tangent. We know our derivative of tangent is secant squared. So it's going to be the secant squared of that sine x times the derivative of the inside, and the derivative of sine is cosine. There we go. Okay, let's take a look at, again, the chain rule in a different context here. So all of these things up here are given. So we have h of x equals f of g of x, find h prime of 3. So the first thing we need to do is find h prime of x. And to do this, we use that chain rule. So we take the derivative of the outer function with the inner function intact, and then multiply by the derivative of the inner. That's a chain rule. So to find h prime of 3, we now plug 3 into each part here. So we're going to have f prime of g of 3 times g prime of 3. And I'm going to just plug in step by step. So I'm going to start with the inner, because that's usually what we do with composition of functions. So the inner is g of 3, which is 4. And g prime of 3 is negative 5. And now f prime of f prime of 4 is 8. So we have 8 times negative 5, which is negative 40. Okay? Okay, so now let's take a look at what this looks like if we're given a graph and we're going to find some derivatives. So if this graph is here, h of x equals f of x times g of x, find h prime of 1. So just like we did in the previous question, we're going to start by just finding the derivative. And then we're going to try to plug in 1. So this is going to be the product rule. So we're going to have f of x times g prime of x plus g of x times f prime of x. And to find h prime of 1, that means we plug in 1 for every x. So f of 1 is, if we look at the chart up here, and I'm realizing right now that my camera is really lagging behind my voice. So I'm going to pause recording for just a second so I can fix that. All right, I think we're fixed now, so we're going to keep going. So we used the product rule, plugged in 1 for x, and now we have to look at this graph and see if we can figure out each of these solutions so that we can multiply and add. So first we find f of 1. These axes aren't labeled, but they go up by 1. So f of 1, we took a look at the f graph. When x is 1, y is 3. So that's the answer there. Next is a little bit more complicated, g prime of 1. So what is the slope when x is 1 on the g graph? So that's this line right here. It's a straight line, and it looks like the slope is down 1 over 1, down 1 over 1. So that's going to be negative 1. And now we need g of 1, which is, again, 3. and f prime of 1. So now we need to know what's the slope of the f function at 1, and it looks like it goes up 2 over 1, up 2 over 1, so that's going to be 2. So we have -3 plus 6, so we have a solution here of 3. All right, let's do the same thing for letter B. This time we have a quotient, and we can't reduce it, so we're going to have to use the quotient rule. So we have low d high minus high d low all over the square of what's below. And now we're trying to find k prime of 6. So we replace all the x's with 6. Okay. And so let's try to figure this out. So g of 6. So 1, 2, 3, 4, 5, 6. So g of 6 is 2. F prime of 6. So what's the derivative of the f? So the thinner line at 6. It's going to go down 1 over 2, down 1 over 2. So that's -1/2 minus f of 6, which is what? 1, 2, 3, 4. G prime of 6. So what's the derivative of the g line at 6? Down 2 over 1, down 2 over 1, so -2. All over g of 6, which we already found was 2 squared. So we have 2 times -1/2, which is -1. 4 times -2 is -8, so it's +8 all over 4, which is going to be 7/4. Oh my gosh, I'm off the screen. We have -1 plus 8 over 4 equals 7/4. Sorry about that. I was off the screen for a second. Now you can see it if you couldn't see any of that earlier. And let's take a look at C. So now we have a composition of functions, f of g of x. So we're going to have to use that chain rule to solve this. So we have p prime of x equals f prime of g of x. So the derivative of the outer with the inner intact times the derivative of the inside. And so now we're going to try to find the p prime of 6. So it's going to be f prime of g of 6 times g prime of 6. So let's do this. We have g of 6 that needs to get plugged in here. So if I go look up at the graph, g of 6 was 2. So we're going to do f prime of 2 times g prime of 6. So g prime of 6 is down 2 over 1, so that's -2. So now all we have to do is plug in f prime of 2. So we go look at the f graph at 2, and we have a problem because the slope on this side and the slope on this side are not approaching the same value, right? Over here on the left, we have a slope of +2. On the right, we have a slope of 0. The limits of the slopes from the left and from the right do not equal each other, so this is not a differentiable point on the graph of f. So this f prime of 2 is not valid. So this actually, p prime of 6 does not exist. Whatever this function p looks like, the derivative at 6 doesn't exist. All right, and there you go. That is how we use a graph to help us find derivatives of complex functions like that. Complex meaning complicated, not complex numbers with imaginary. But that takes us to implicit differentiation. So we are pretty used to, at this point, explicitly differentiating functions. And that's whenever we have an expression or an equation that's already solved for y equals or has function notation. The right side only has x's. We know how to take derivatives here. But what if we have functions that look like this and we have to implicitly differentiate? So if it's an implicitly defined function, it means it's not solved for y equals or there's y's on both sides. The x and the y's are intertwined. All right, so let's figure out how we can differentiate when we have to deal with implicitly defined functions. So let's take a look at this first one. Y cubed plus y squared minus x squared equals -4. So first up, we're going to differentiate with respect to t. So that's kind of a weird ask. There's not even a t in this equation. There's only x's and y's. So what that means is we differentiate each term like normal, pretending like we're differentiating in terms of y. So for example, for this first one, we have y cubed. So we're going to do 3y squared, which is our normal way of differentiating a y. You know, we use the power rule. But now think of that y as like a separate function. So the outer function was the y cubed, and we did 3y squared. So we still have to multiply by the derivative of the inner. You know, think about our chain rule. So now we're multiplying by the derivative of the inner function, which was y. And since we're differentiating in terms of t and not in terms of y, the derivative of y is dy dt. You'll see that several more times here. So the derivative of y squared is going to be 2y times the derivative of y, which is dy dt, minus the derivative of x squared, which is 2x, times the derivative of x, which is dx dt. And that equals the derivative of a -4, which is 0, like normal. So we don't have any variables over there. Okay? So each term had to be taken separately here. So let's try again. So in letter B, we're going to differentiate with respect to w. And each derivative will have d blank dw as part of the derivative. So for this first term, now we have 3y squared times dy dw, as we're differentiating in terms of w. The second term is going to be 2y dy dw. The third term is going to be -2x dx dw. The -4 turns into a 0. So you can see it's almost the same exact answer as part A. We just have dw's instead of dt's. Because now we're differentiating with respect to w. You always have to pick one variable that you're differentiating with respect to. In a normal version of explicitly defined functions, we're usually differentiating with respect to x. And that's why we don't have to worry about it. You'll see that when we get to part C. Let's try to differentiate this one with respect to x. So since you must apply the chain rule, each derivative will have d blank dx as part of the derivative. So let's do this again. So again, we're going to have the same answers as we did for the first ones, but this time with dx in the denominator. So we're going to have 3y squared dy dx plus 2y dy dx minus 2x dx dx equals 0. And this time, you will notice that whenever we actually used the variable that we're differentiating with respect to, the derivative is dx dx, which cancels out and just leaves you with 1. Now, we don't usually write dx dx, but that's really what's happening every time that we use the variable that we're differentiating with respect to. That's why for all of our normal derivatives that we've done so far this year, we haven't had to think about dx dx because it was always implied, it always equaled 1, it always went away. When we're looking at other variables, though, we have to remember to put the dx at the end if we're differentiating with respect to x. So this is really 3y squared dy dx plus 2y dy dx minus 2x equals 0. The dx dx goes away. So now we can use algebra to rearrange and solve for the actual derivative of this. Solve for dy dx, which is how we like derivatives to be, which is very interesting. So let's try this. So we have that equation. What we do is we move everything that doesn't have a dy dx in it to the other side. So we're going to start with 3y squared dy dx plus 2y dy dx equals positive 2x as we add 2x. And now we're going to factor out a dy dx from each of these terms. And then we divide 3y squared plus 2y to the other side. And we get our dy dx by itself. So we have 2x over 3y squared plus 2y. So that is our derivative. All right. So that's an introduction to implicit differentiation. We have a couple more examples that we will do together to work through this. So let's keep going. Next example, find the derivative dy dx. So we're going to do the same thing as before. We take each term and separately take the derivative and use dy dx when necessary. So for the first one, for x squared, the derivative is 2x. We don't have to write dx dx. We're differentiating in terms of x. So the derivative of x squared is still just 2x. The second term is a product, so we have to use the product rule. So we would have x times the derivative of y, which is dy dx, plus y times the derivative of x, which is just 1. And then we subtract the derivative of y squared, which is going to be 2y times dy dx. And that equals 0, because the derivative of 3 is 0. We're going to solve this for dy dx now. So let's move everything that didn't have a dy dx in it to the right side. So we're going to have x dy dx minus 2y dy dx left on the left. On the right, we're going to have negative 2x minus y. And I can factor out a dy dx. And then divide by that. So we end up with negative 2x minus y over x minus 2y. Okay, next question, we're going to do the same thing. So on the left side, we have a fancy pants product rule here. So we're going to have to do the first times the derivative of the second. So the derivative of sine y is going to be cosine y times the derivative of the inside, which is dy dx, plus sine y times the derivative of cosine x, which is going to be negative sine of x, times 1, so that's it, equals, and the derivative of root 3 over 4 is 0. We're trying to solve this for dy dx, so I'm going to move this stuff to the other side. So we have cosine x cosine y times dy dx equals, this was negative, so now it's going to add, and we get a positive sine x times sine y. I'm just going to write it in x and y alphabetical order because that's the way I like it. Then I'm going to divide by cosine x cosine y, so we have dy dx equals sine x sine y over cosine x cosine y. That is a perfectly valid and acceptable solution. However, we could go one step further if we wanted to, because we have sine over cosine of x's and sine over cosine of y's. That really is the same as tangent of x times tangent of y, if you want to get fancy. Okay? So there's our solutions to A and B up here. Let's keep going. We got one more section of examples, A, B, and C. And it has to do with a graph that looks super weird, like this. And this keeps going in these directions. And this graph is of y cubed plus y squared minus 5y minus x squared equals negative 4. Now this is definitely not a function, and it's going to be very hard to graph this on your TI 83 or 84 graphing calculator. So we're not even going to try that. But just know that this is true, and you could use Desmos and graph this if you wanted, and you could see that it really does look like this. But this is going to be important. This picture is going to be important as we get to parts B and C. So let's see what we got here. First, of course, find the derivative. So we're going to use our implicit differentiation rules here. We're going to have 3y squared dy dx plus 2y dy dx minus 5 times y. So the derivative of 5y is going to be 5 times the dy dx minus 2x, no dy dx or dx dx there, equals 0. And now we want to solve for dy dx. I'm going to factor dy dx out of these first three terms. And I'm going to move this 2x to the right side. And I'm going to divide by that. So we get dy dx equals 2x over 3y squared plus 2y minus 5. So that's our derivative. Still a little crazy because it has x and y in it, but it works. So let's take a look at part B. Write the equation of the tangent line to the curve at the point 1, negative 3. So let's take a look at this graph up here. 1, negative 3 is right here. And so we know that there is a tangent line there. It's going to look something like this. I couldn't tell you just based off the graph what the equation of that line is, but we can figure it out. So first of all, if we're going to have the equation of a tangent line, that tangent line is going to have a slope, right? So to find the slope, we are going to use this formula. We don't have 2 points to do y2 minus y1 over x2 minus x1, but we do have the derivative of this whole curve looking thing. And we have an x value and a y value. So let's plug that in so we can figure out what the slope is at that point. So it's going to be 2 times the x value over 3 times y, which is negative 3 squared, plus 2 times y, which is negative 3, minus 5. So we end up with 2 over 3 squared is 9, times 3 is 27, minus 6 minus 5, which is 2 over 16, which is 1/8. So our slope is 1/8. That tracks, it's positive, and it's not very steep. So that looks like it could be the slope of this line. Now, though, it wants us to find the actual equation of the tangent line. So this takes us all the way back to Algebra 1 when you learned about y equals mx plus b. And we now have a slope. We have an x and a y that we can plug in order to solve for b. So we have 1/8. Our x is 1. Our y is negative 3. And we're going to solve for b, so I'm going to add or subtract 1/8 to the other side, and I get negative 25 over 8 is b. And so now if I go back to the original, I'm plugging in the 1/8 for the slope and the negative 25 over 8 for the b, and that is the equation of our tangent line. Okay? Question C. Find the coordinates of the points on the curve where the line tangent to the curve is vertical. So let's take a look up here again. This time I'm going to write in orange. If our tangent line is vertical, it should be right here, right here, right here, and right here. So we should have 4 different points where the line tangent to the curve is vertical. It's our job to find them. And to find them, we think about, well, what do we know about the slope of vertical lines? And the slope's undefined, right? If we have a vertical tangent line, that means that the slope is undefined. And if a slope is undefined, that means that we must have divided by 0 in our derivative, right? So if we're dividing by 0, then we're going to have an undefined slope. So that means that our 3y squared plus 2y minus 5 must equal 0. The denominator must equal 0. That's what's giving us this vertical slope. So we can factor this to 3y plus 5 and y minus 1. And we end up with y equals negative 5/3 and y equals 1. Okay, so that only gave us 2 y values, and those 2 y values are apparently where these vertical tangents happen, and it makes sense if you think about y equals 1 must be representing this point and this point. Those both must have y values of 1, and this point must have y values of negative 5/3. So then we have to figure out the actual coordinates of the points, not just the y values. So how are we going to do this? We're going to have to go back to the original, which was x squared. No, it wasn't. I went back to a different example. It's y cubed plus y squared minus 5y minus x squared equals negative 4. And what we're going to have to do is plug both of these in and see what we get for x. So let's start with the negative 5/3. Okay, so I plug that negative 5/3 in. I did the math in my calculator. I solved for x squared, and I got the x squared is 283 over 27. So if we square root that, we get x is plus or minus the square root of 283 over 27. I need to do the same thing when x is 1, or sorry, when y is 1. So I'm going to plug that into this. So we have 1 cubed plus 1 squared minus 5 times 1 minus x squared equals negative 4. 1 plus 1 minus 5. Move that to the other side, and I end up with x squared equals 1. So x is plus or minus 1. So our 4 points are, if we start with these ones, we have a positive 1 for the x value that goes with a 1 for the y value. We have a negative 1 for the x value that goes with that same 1 for a y value. Then we have an x value of square root of 283 over 27 with a y value of negative 5/3, and an x value of negative square root of 283 over 27 with a y value of negative 5/3. So there's our 5 points where we have a vertical tangent line, and that matches up exactly with the 4 places up here that we said they should happen, okay? So that is the end of the notes on lesson 2.2, the chain rule and implicit differentiation. Let me know if you have any questions, and thank you very much for watching.